Hello everyone. The topic of the poster that my team is going to present is controller and row decoder design for banked versus non-banked architecture. The authors of this poster are Rishabh Kumar, Saranjitha, Raisana Hossain, and myself Manoshi Barua. We know that the SRAM array consists of a matrix of bit cells that store information in the form of charge. The given diagram is a block representation of row decoder and controller with the SRAM array. The row decoder activates the word line and the column decoder activates the bit line. A controller can generate control signals such as internal clock, read enable, sense enable, etc. In this poster, we have presented a banked architecture where the memory is divided into banks. With this architecture, we will able to achieve significant power reduction with some penalty in area and timing. In the conventional non-banked architecture of row decoder, there is a global control block that contains one 3:8 pre-decoder and three 2:4 pre-decoder that decodes the n address line for 2 raised to power n number of rows. The clock generation circuit generates the internal clock signal that is responsible for activating the rows. The pre-decoders assert their output depending on the combination of address signal inputs. The row decoder decodes a particular word line of only a specific row, while the rest are put off depending on the combination of decoded signals generated from the pre-decoder. Each word line is driven by a decoder level shifter that drives the corresponding word line from low logic power supply domain to higher memory supply voltage domain. The generation of word line consume a considerable part of the total memory access time as designs move to shorter bit lines due to increased leakage and performance demand. When the internal clock signal will be high, it will activate the clock codec signal, which will generate the word line for the selected row.
Hi, myself Rishabh Kumar and I will walk you through the banked architecture that we have proposed. Here is a global control that have inputs like address input, external clock, chip select signal, test mode signal and write enable signal. This generates internal clock and the bank select signal, which is fed to the local control logic which is shared among the two banks. Depending on these signals, one of the bank will be selected and further a word line of a specific row will be selected. This is logic inside the global control. Reset here is used to reset the internal clock which further resets the word line. This is bank select logic which have 3:8 decoder. Depending on these 3 bits, one of the bank will be selected. This is write enable block. The main function of this block is to provide the control signals to the array to enable either the read write operation. This is local clock generation logic inside the local control. The given circuit generates clock top and clock bottom which are to be mixed in the post decoder stage corresponding to the two banks. Clock top and clock bottom will be going to the local control circuit's top and bottom bank respectively. We have the same local control circuit shared among the two banks, so by using the combination of the two bank select signals BS1 and BS2 and the internal clock, we generate the clock top and clock bottom. BS1 and BS2 are the bank select signals generated by the 3:8 decoder present in the global control block corresponding to the topmost bank and top second bank. Bank selection signal of pre-decoders. The read enable signal is an active low signal going into the NOR gate present in the latch. Read enable goes low if one of the two banks needs to be chosen. If one of the banks are selected, then the read enable goes high, which resets the latch outputs in the pre-decoder block to 0. So whenever 6 of 8 banks are not to be selected, the pre-decoder outputs will turn off, thereby avoiding the toggling in the post-decoder stage and saving a lot of power in the row decoders of the 6 non-selected banks. Signal flow for word line generation using bank select signal. Note in this case all address bits are enabled high. This is fourth bit of address bus. This is external clock which triggers the active low clock int. The active low internal clock and 3 MSB bits of the address bus will be responsible for selecting one of the bank select signals. This further enables selection of local clock row deck, and finally specific word line will be selected. In this case, we have shown timing diagram for critical path. The data presented here explains the delay breakdown for banked and non-banked architecture. There are three segments of delay, that is clock to clock in delay, clock in to clock row delay, and clock row to word line delay. The clock in to clock row delay is less for non-banked architecture due to less loading. The clock in to clock row delay for banked architecture increases significantly since the clockant has to travel to all the local control blocks for generating local clock. The overall delay for non-banked architecture is 702 picosecond, and for banked architecture it is 753 picosecond. To conclude this study, let us analyze PPA results of banked and non-banked architecture. This data is presented for PVT corner SS 1.08 volt and 125 degrees Celsius. Clearly, we can see that banked architecture gives an advantage of the significant reduction in power consumption. The area and delay of the control and row decoder part of banked one are higher than that of its non-banked counterpart, so it falls behind the conventional architecture on timing and area aspects. Thank you.